Hello and welcome to the Energy Resilience Lab. Our lab is dedicated to giving you the knowledge, skills, and the encouragement that you need to become energy resilient and energy independent. Our show consists of three formats. The first one is informational, so that's where we'll just be training you on something. Second is interview style, where we will interview different people that are in the market and people that have already become energy independent and energy resilient. And then third is energy storage news. So that will be different breaking news with regards to natural disasters or man-made disasters that affect our lives with our energy that we consume. And then also any new products that are coming out that are disrupting the market and helping us become more energy independent, either by getting less expensive or by being able to do more things with a smaller system. Anyways, today's, just to get moving here, today's show is going to be more knowledge-based. So last week we went into what energy is and the different types of energy, and a little bit how it can be stored and work, and kind of just defining to you what those things are so that we can be more cognizant of what's going on with regards to power and energy. Once we do that, you'll be able to notice things around you that may be taking more power or energy, and you can use that to become more energy independent by conserving on those things or by changing how you operate those devices. So today we'll just start going through power and work. I'm going to be reading a good portion of it. I got it from various sources, from the internet, just searching and trying to find better information for you guys that's more bite-sized, so you guys can move forward learning what power is and how it's calculated, and then that will help you learn how big of a system that you'll need for whatever level of resilience you're trying to get to. So today is power. So power is related to other quantities, for example, so the power involved in moving a ground vehicle, so a vehicle that drives on the ground, not an airplane, like a car, is the product of the aerodynamic drag plus the traction force on the ground and the velocity of the vehicle. So if we're looking at a system, a control system, a controlled region that makes up a energy and power system like a vehicle, we all understand that as you're driving, that the air moving past the vehicle causes drag, so that tries to slow you down. And then the traction force on the ground is what you need to be able to push through all of that load that's generated going into the air. And then all of these, this whole system is related to the velocity. So the faster you go, the more power it takes to sustain that speed, which in turn you are using a larger amount of energy. So in the case of an electric vehicle, the faster you go, the less range you get. In the case of a gas vehicle, it's the same. So the faster you go, more fuel you consume. So the more frequently you have to stop to get more fuel at the gas station. In the case of a motor, the output power of a motor is the product of the torque that the motor generates and the angular velocity of the shaft. So if you've worked with a small engine before on a lawnmower or on some other small household device, weed eaters, all those things, the amount of power that it's using is the torque it's generating and the speed. So the faster you go, the more power it's consuming, and the higher the torque. So if you're loading it up, like in the case of a lawnmower, if you're actually mowing, then it needs to add enough power or work to the system to be able to cut all of that grass and clip it and push it into the bag in the case that you have one. And so if you want to know how much power that's using, you could measure the torque and the speed that the system is operating on. So now if we get into electrical elements like a heater or something, electrical device, the power dissipated in an electrical element of a circuit is the product of the current flowing through the element and the voltage across the element. So not a lot of people are probably have heard that before or have had to work with that, but essentially that's what we all do in energy storage systems. That's how you calculate how much power the system is taking, is you'll just measure the voltage and measure the current, and that gives you the electrical power that's getting consumed. If you want to look at it as a system, you have a small ceramic element heater. Plug it into the wall, turn it on high, it will usually consume between 1300 and 1500 watts. So the voltage in the wall is usually 120. In America, I believe in Japan, it's around 80 volts. And then in most of the rest of the world, it's 220 volts. And then the frequency on it with AC power is different at different locations as well. But all you need to know is the voltage and the current equals the amount of electrical power that's consumed. So if you were to get a power meter, the Sense home energy meter, it'll tell you what the voltage is on the two legs in America. So there's 220 volt AC legs that can be used with each other to give you 240 volts. And so the amps across each of those legs to neutral or to each other is the amount of power you're consuming. And the home energy meter shows you that just in a total value, but you can dig in and get the voltage and power and current if you're interested to know how much it's taking. So the dimension of power is energy divided by time. So it's joules per second, so 1 watt. In the international system of units, the unit of power is a watt, which is equal to 1 joule per second. The common and traditional measures are horsepower, comparing to the power of a horse. 1 mechanical horsepower equals about 745.7 watts. So since all of the systems before the 1900s were run on horses mostly, so human power or horsepower, when we started to quantify things in physics, they started with 1 horsepower. And that is a defined amount of power, and it's enough to pull a small carriage. Moving forward in time, we've learned a lot more, and we're using a lot more complex systems to do the work that we have to do and to utilize power. So we've moved in to a more continuous power analysis. And so if we just break it down, then it's just one joule per second is a watt, and then energy is all of those joules per second added up over a specific amount of time. It's usually measured in kilowatt hours. It's just convenient because that's kind of a convenient amount for a home or other things to use. The smaller systems are just in watt hours, which is still helpful. So 1 mechanical horsepower is 745.7 watts. And so if you want to calculate between the two, you divide the amount of watts by 745.7, and that gives you how many horsepower. And so for an electric motor, there's going to be efficiency factors and other things built in, but to get an idea of how many horsepower something uses, you can take the power and divide it by 745.7, and that'll give you the mechanical horsepower. This is usually helpful for something like driving like vehicles. So a lot of people enjoy the horsepower rating on their vehicle. You could also rate it in power. So in the electrical vehicles, they'll tell you how many horsepower it is and how many kilowatt power it is. And so getting back to a watt, or to horsepower, you can go back and forth to understand your system better, whichever one you're more comfortable with. With that system, we're able to understand how much power you're using, and then over time how much energy. So just to give you an idea, in a vehicle when you're cruising at 65, 70 miles an hour, it usually takes around 20 horsepower, which is 16 kilowatt power. And so if you multiply the number of hours that you're driving per day by 16 kilowatt, that would give you the kilowatt hours of energy that you're consuming approximately on the freeway. So this would just be an average car, maybe a small SUV, not a very large one, and also not a very small car. So they're going to use varying amounts of energy, but that's just kind of gives you an idea. So power in mechanical systems, like we're talking about in vehicles, is a combination of force and movement. In particular, power is the product of the force on an object and the object's velocity, or the product of the torque of a shaft and the shaft's angular velocity. So in an engine, you have a crankshaft that's spinning. That's quantifiable. You can measure how many RPM it's running at, and then you can measure the torque with a torque instrument, and that will tell you how much power you're using in a mechanical system. When we get into electrical systems, there's a few equations that are helpful. So power equals current times voltage. That's the one we already talked about. If you mix that power equation with Ohm's law equation, you can get different derivations of power. So another one would be I squared R. So it is current squared times the resistance, or voltage squared divided by the resistance. And how this is helpful is usually in a system when you're looking at sizing it, especially in electrical systems, the lower the voltage at the same power, the higher the current has to be. And so when you're sizing a system, going up in voltage reduces the number of amps. And so if we use this equation, that power equals the current squared times the resistance, that means that every time you increase the current, your losses are exponentially more. So every time, so if you have 2 amps, then that would be 4 times the resistance. If you have 4 amps, then it would be 16 times the resistance. So you can see that the losses in your system are a lot larger. You can circumvent that by making the resistance very small, but when the current is squared, it's hard to overcome that. And so the higher the voltage of the system, the less losses you're going to have. We get into other issues in that, because changing the voltage doesn't only fix problems, it can actually cause more problems, because as soon as you get above around 60 volts, that's considered lethal voltage. So that voltage can kill a person, and so you have to be very careful in the engineering of those systems. So electric vehicles, they're usually between 300 and 500 volts on the battery. I believe in the new Hummer, they went to 1,000 volts, and that just makes it so you can have less amps in running through the system, and you'll be able to get a large amount of power. And so that's convenient because it just minimizes all of the losses in the system, minimizes the system control element sizes, which can control cost a lot. Now getting into duty cycles. So when you have electrical heating devices, usually a lot of them aren't fixed amounts of power. So in the case of the ceramic heater, it is a fixed amount of power. It self-regulates when you have a ceramic element. But in other things, like in your oven, it does have fixed amounts of power, but the amount of energy that you're adding to the system can be changed by changing the duty cycle. So something we need to learn is the duty cycle of a system. So if you're running a furnace in your home, which you might be able to hear behind my studio here, the furnace just turned on. The furnace only turns on for a certain amount of time. So there's a thermostat upstairs in this case, and it's just measuring the temperature. And once it gets out of the dead band, the area where the furnace is just waiting, so it gets below the set point by 2 degrees, it will turn on, and that causes the furnace to turn on. And then it will heat until it crosses another set point, and then it will stop heating. And then it'll wait for the home or the region to get cool again. And so the duty cycle would be how much time was the furnace on compared to the amount of time, total time, that it was on and off. And that will give you the duty cycle. So if it's on 80% of the time, that would be a 0.8 duty factor. And that's just good to know, because when you're looking at power, like if you get the home energy meter, you'll be able to look at the power and you'll see that it gets very high and then it will drop low and it'll go high again, and you'll see different patterns in the power. And so furnaces are like that, where they turn on, run for 10-15 minutes, turn off, wait for 5 or 10 minutes depending on the cooling load or of your home. But that duty cycle is going to vary, and that is what allows your home to stay at the temperature that you would like without keeping a furnace running all the time at kind of a partial power or something like that. So it just allows it to turn on full power and then be off, turn on full power and then be off. So on your air conditioning, it works the same way, and also with your oven. So if you turn your oven on to 400 degrees, you'll see the element goes kind of orange, and that's because the energy is going through that element and it's causing it to heat up in the oven. So it will get hot, it's adding energy, and then it has a temperature sensor monitoring the temperature. And so when it gets above the set point, it will turn off the element and just let it sit for a while. Element back on, and then it will let it sit off again. And so that time of being on and off is the time of the system, and the amount of time on divided by the total time of off and on is the duty cycle. So when you get into more of your home's power data, you'll see that there are these big spikes, and a very large contributor to that would be an oven. They can be 3K or 6K elements. Another one would be clothes dryers. They will run at 6 kilowatts sometimes 3 kilowatt, depending on just the size of the element. And if you have an energy saver mode on your dryer, it's usually just a different thermostat. So you're just taking it to a different temperature and then letting it cool. So the bands of heating are less, so your duty cycle is less in the energy conservation mode. So it takes a longer time to get your clothes dry, but you're able to use less power, less energy, sorry. The accumulated power of the whole cycle in energy will be reduced in the energy conservation mode, but the time and the duration that it needs to cool will be extended. So that's how those systems work, and when you're monitoring your power, you'll see that that's what it's doing. And so how that relates to us when we're trying to become energy resilient is we need to see where these peaks are. And so in my case, we have a lot of electrical systems in our home, and we will see, I believe the highest power that we've seen in a few years is about 24 kilowatt power. And that's just when the perfect storm happens. So you have all these duty cycles acting. So all of these systems in your home turning on and off. And if they all turn on at the same time or just overlap each other, then that's where you get these very high power peaks. And that power peak for me was probably only 30 seconds anyway, but that's just something that we need to understand, because if you want to power your whole home, you need to have enough power to cover all of those loads if they all were to line up and stack powers. And so systems get pretty big when you want to do that. One way to get around that, to make a resilient system for your home and not have to have that much power, would be to have a load shedding device. Turns off certain loads when the power goes down, or you can have a critical loads panel, and that's where your energy storage system will just be hooked up to a separate load center in your home, and you just put all the loads, all the devices that you want to work when the power goes down into that panel, and then the other panel, that one will stay connected to the grid, but it will just go down automatically since it's not connected downstream of the energy storage system. So as we dig deeper into power, there's a lot of intricacies that you'll find in your home. And so if you dig into your power bill, in some cases you'll see peak power charge or peak demand charge. Sometimes there will be multiple, but that is the highest power that was sustained for 15 minutes in your home or your business. The problem with using the data from your power meter is that usually the power company is less concerned about these very short 30-second spikes. And so the peak power that you actually sustain for a short amount of time will be much higher than what your bill indicates. So that gives you, that's a problem for solar companies and energy resilience people that want to build out UPS systems. They can't just look at your bill like they would in an AC coupled solar system to offset your bill. They have to know how much power you're using as well. And so the more information you can have, the more you can help them size your system, or in the case that you're working on a system, you need to know all of this to be able to size it properly and not have it turn off. The concern is if you don't have a large enough inverter and you're connecting it to too many loads, as soon as the power goes off, it may be fine when the grid is on because you're passing the grid through to cover. The grid's leading, powering all the equipment in your home. As soon as that drops out, your inverter needs to cover all of those loads. And commonly when your home turns all the way off, a lot of your control systems will start asking for power, essentially. Your furnace will be asking for power, your electric water heater, all of these things will be cooling off and they'll need to use energy. And so it's kind of the perfect storm of where your home will demand the most amount of power in the event of a power outage that's longer. Once your system turns on and starts operating for a while, then all those systems will get back up to speed, so they won't all be on at the same time. So then the power demand goes down. And so that is sometimes referred to as dark start, and that's where everything's dark, everything is out, and you need to be able to start all the equipment in your home in one shot, and that's what the inverter has to handle. Usually with transformer-based inverters, they can do 3 to 4 times their nameplate power in inrush current. So they're very good for high inductive loads and for large loads. But when you get into transformerless inverters, you do need to watch that because they'll usually do 50% more power than what their nameplate is for an inrush to 100% more. So if you have an 8K inverter, you'll just get 12K power inrush to jumpstart all your devices up to 16 kilowatt. And you can add on to that. A lot of inverters can work in parallel, and so it keeps compounding. So every inverter increases the system by the amount of the inverters. So it doubles with the second one, and so on. So that is kind of how duty cycle and power works. And as we've went through this, I've tried to explain to you the different different systems in your home and how much power they use. It's really helpful for you guys if you guys can get into your power usage either by purchasing a power meter or by like a home power meter that measures everything, or just by buying a kilowatt meter. So if you go to the store like Walmart or Amazon, they have these meters. The old brand name was Kilowatt, and it's a meter you just plug into the wall and then you can plug devices in behind it, and that will give you the peak power, the amount of energy that was consumed, that device consumed. And so what that does is you can just isolate systems. So like I have a deep freeze freezer. That freezer uses about 70 watts continuous when it's up, and the inrush on it is about 1,000 watts. And then I also have a regular refrigerator, and it runs at about 120 watts, and the inrush to start the motor is about 1,500 watts. So as you'll see, if you do dig into your power bills and power data, you'll see different systems and how much power they use. So the newer the equipment, the newer refrigerators have less and less of a inrush, so they're using VFDs to start the motor, and they're able to change the velocity of the motor, angular velocity. And so in doing so, they can reduce the amount of amps that have to be drawn for refrigerators and things. Great. So on the small scale, getting just a kilowatt power meter, plugging in your refrigerator can tell you how much power and energy you're using, and then from that data you can calculate how long it will last and the amount of power that's required for it to start. So that'll be very helpful as you start to break down systems and make them more energy resilient. In the next show, we have had some questions. Thank you all for asking your questions on energy storage. We'll be making an episode on questions and the answers to those questions. It should be fun. So I'm glad you guys are reaching out and giving me your questions so I can work on those. Like always, please like and subscribe to the channel, and please share it. It's really a great time to start becoming more energy resilient and independent. Battery systems especially are becoming more and more viable in the market with the cost of energy going up so sharply. Especially as the country goes away from using coal, there's going to be cost increases in power. And so if you're ready, it's a good time to get in and start using energy storage systems to self-consume. I will do an episode going forward on AC coupled systems, DC coupled systems, and kind of the pros and cons of each. There are a lot of people that get solar just to become energy, so net neutral essentially. And so what you're doing when you do that is you're just taking the solar power and exporting it immediately to the grid. And then the grid is giving you credits so you can use them at different times of the day. The amazing thing with energy storage systems is you can self-consume. So you can take in all the energy that you produce from your solar array, put it into a battery, and then use it. And so if the system's sized properly, you can reduce your consumption to zero. So the inverter, you'll always be connected to the grid. There's no reason to disconnect from the grid. There's a small charge that they charge you no matter what, even if you don't use power. That's like $13 to $20. But having it there is amazing for when you need it, because systems can go down. So that's good to have always connected. But being able to self-consume allows you to have an energy storage system on site to generate your own power. And that means your system is ready to go all the time because it's always working. So it's taking in the solar energy, putting it into the battery, and then covering as many of the loads as it can through the night or over days if you're building a very large system. And that is an amazingly resilient system because you've got the system always operating, so everything's aligned and working. And so in the event of a power outage, it's just another day for your energy storage system. The system is turning on, collecting energy from the sun, and then powering the loads of your home. You can run into issues with the power like we talked about if you have too many loads connected to it. If you do shed loads, then you'll be able to get the influx of energy from when it's available. To make it totally resilient like we've talked about, it is needed that you get a generator connected to your system. A lot of the energy storage systems are compatible with generators. You can even use a generator that you just pull start, like a site power generator from Home Depot or Lowe's. Connect that into your system if it's split phase 240, and that can add energy to the system. In doing that, when there's a storm or a long time without sun, then the battery and generator can work together to give you all the energy that you need to keep the system up 24/7, but to minimize the fuel. So if you have a standby generator, it just runs. So if the power goes out for a week, it'll just keep running and keep consuming fuel. Some estimates are that you will save 80% of the fuel that a standby generator would use by just using an energy storage system. So when you're using an energy storage system, it only turns on to be able to charge your system, and that also is much more quiet. So you can have a system that's quiet, more energy efficient, and more robust just by getting a generator and an energy storage system. Adding the solar component reduces fuel consumption over time, and it also makes it more robust because the fuel source is the sun and it's not going away. As for fuel like gasoline and diesel, If you have to store those, gasoline's kind of hard because it's hygroscopic, so it takes in a lot of water. So you have to watch that and make sure it stays fresh, and you can add things to stabilize it. And then diesel fuel, you can get algae and things that will grow in the diesel fuel that can cause problems. And so those systems are a little bit harder to keep going for a long period of time. The other option is propane, and propane tanks are very useful. It is liquid, so that's good. You've got pretty good energy density, but they do take up a lot of space. You can bury them to get more capacity with them, but that's the other option. So thank you all for tuning in. If you guys have any questions or concerns, please tell me, or if you have any more information that you'd like to share, please drop it in the comments for all of us to consume, so we can learn more about these systems and the requirements of our homes. Thank you. Please like and subscribe. We'll talk to you later. Have a wonderful day.